y'all. Barely Berry Jr. here, back as promised. Looks like the audio is okay. Whoever joins, be sure to let me know if there's any issues, but it seems fine on my end. This week was my first week in graduate school. It was cool. Of course, most of the stuff is introductory stuff and starting to get the classes started with my TA duties and things like that. So fun learning about the research I'll be doing. I'll be doing a research course this month. Um, I'm a Palace Fellow, so starting to talk about some of the teaching I'll be doing in the future. So good stuff. And in my foundational class for physics, where we review the undergraduate stuff, we talked about a few interesting things. Also, talked about a few interesting things in my graduate class. So in classical mechanics, so I'm doing classical as a review for undergraduate, as well as classical actual graduate level stuff where we're starting to get into multiple particles and things like that. So I'll talk about a few of these things. So let's say we have a box on a ramp. So, or block, a mass on a ramp. And one of the things that we can do in classical mechanics is if we were to take this block, this mass, M, and release it, we can calculate its trajectory down the ramp. We can calculate how much it'll accelerate. We got to calculate the speed it'll reach at the bottom and things like that. So we'll do some of that. So what we'll do is calculate the velocity at the bottom from the top. So assuming that we let it go from the top, it's been traveling a little bit, and this is our velocity here. And velocity can be written as an arrow, or it can be bold. So I might go back and forth. And it looks like the bold is showing clear enough as I have to remember to adjust my pressure. So we'll see that from the top of the structure, let me actually let me adjust my template a bit. A little bit better. So let's see that actually let me adjust just one more time. So let us see that the initial velocity, V naught, is 0 meters per second. Let's say that the mass is 20 kilograms, that's standard SI units. Let's say the length at the bottom here of the box is 10 meters. Let's say that the height of the triangle of the ramp is 6 meters. And we may or may not do a friction. So there's a coefficient of friction depending on the material and things like that. Let's say the coefficient of friction is 0.5, so we'll see about that later. So the first thing is to do your free body diagram. And my professor in class did an interesting method, which is to do it separately, which I think would be more difficult on this one. The one where he did it at the block was on a pulley. So I'll just do the regular one here. So what we'll do is first make a coordinate system. I'll make a coordinate system aligned with the ramp that we're on. So we'll call up and down the ramp X, and vertical to the ramp or up into the air directly off the ramp Y. So what we have here is that gravity is pulling directly down. This is F equals mg. But the thing is, this force is going to be split into its x and y components because some of the force is going to be moving the mass down the ramp, and some of the force is going to be pushing into the ramp. So what we can do this is we can have our Fy that's going into the ramp, and we can have our Fx that's going down the ramp. Another thing we'll also have here is the normal force, which is the force that's causing the block to not just collapse through the ramp, being pushed back up from the ramp. And then we have our friction force, which may or may not be zero depending on how we set the problem. I think in real life, you'll always have some kind of drag. I suppose you can put the block in the vacuum uh, and magnetically or otherwise hover it over the ramp. I don't think there'll still be friction. Maybe there's some kind of magnetic friction if there's any charge in the in anything while it's moving. But for now, we'll assume an idealized situation where there's no friction. And now, one interesting thing about this is if you have a block like this, you can recognize that this angle here is the same as that angle there. So one way we can look at this is if this angle was to go up to 90 degrees, gravity will still be pulling down, and we see this sideways angle will go all the way up to 90 degrees as well. And conversely, if this goes all the way down, so it's, there's no ramp, it's just flat, then this will close all the way down, so there's no angle there. So you can see how those two are directly related. Another thing we can notice is if I was to raise this ramp all the way so it's vertical, the block would just fall straight down. It won't be affected by, no force would be going to the ramp at all. It would just be falling. And the only trigonometric function that would allow us to have 100% of the vector at 90 degrees is sine, because sine of 90 is 1. But at 90 degrees, sine will give us 100% of that vector. So that means that going down the ramp, Fx is F sine theta. And by the same token, if the ramp was tilted up 90 degrees, cosine would give us 0. And of course, this blue one here, it'll be horizontal to everything that's going, so 0 will be going in that direction. So Fy equals F cosine theta. And this gives us the amount of the force of gravity that's directed into either direction. Another thing we can look at as well is to get the length of the ramp. So we know from trigonometry, x squared plus y squared equals r squared. Like a triangle or what have you. So 8 squared plus L squared equals R squared. So that means that 6 squared plus 10 squared equals R squared. So that equals 136. So R equals the square root of 136. Now I'll go ahead and get a relatively exact amount with my calculator, which I went and got so I can work on some homework problems, even though most of them been doing derivations, so I haven't had to use it yet for my homework. came up to 11.7. If I was to round a little bit, meters. And now I'll check, round it a little bit when I did it the first time, but 7.7 is good. So now we have that. We'll probably need that later for something. So what we can do to get the velocity is to remember that F equals ma, which is Newton's second law. So we have our F. The F that's going to be pushing it down the slope is Fx, which is going to be F sine theta. So that means that the acceleration down the ramp is going to be F sine theta divided by the mass, which is going to be the mass times gravity sine theta divided by the mass. So it's going to be gravity sine theta meters over second squared. So that works. So let's see what this is. So we're using in class 9.81 meters per second squared sine theta. And we need to figure out what theta is. So we can use tan inverse of theta equals opposite over adjacent. So tan inverse opposite is H over L. So that's tan inverse 610. So theta is oh, second tan 610. So that's 0.54 radians. It's about 31 degrees. So A equals 9.81 meters per second squared sine 31. So that equals 4.2, let's say 4.3 meters per second squared. Now I'll put the negative there to denote that it's going down. Right, so we have that. And looking at my notes, yeah, a little bit the first time, but yeah, about that amount. Looks pretty okay. And what we can do to get the velocity, we can do some integration. I was about to say which is always fun, but I would say was often fun. So acceleration, in this case, I'll call this a prime. So if I was to integrate acceleration, It'll give us velocity, which is a prime t plus v naught. And we'll also integrate this. It will give us xt equals a prime t squared 1/2 plus v naught t plus x naught. And we know that the full distance is 11.7 meters. So what we can do here is figure out how long it takes for the block to go down. And we can use that to plug it into here to get the velocity. So what this will give us is 1/2, I got a 4.3 meters per second squared, t squared, v naught is 0, starting from rest. And I'll denote the starting point as 0 as well. So what I'm saying is this is 0 meters and this is 11.7 meters where it ends up. So if I were to divide that, I have 2.14 meters per second squared equals, we can actually drop the negative here, 11.7 meters. T squared is still there. So t squared equals 11.7 meters divided by 2.14 meters per second squared. So that's going to be about 5.46 seconds squared. So t equals about 2.33 seconds. So did a little bit of rounding before, that's about what it is. So now I can go ahead and do like I said and plug this into here. And we can say V at 2.3 seconds equals a prime t plus v naught, which equals 4.3 meters per second squared, 2.33 seconds. And we know that this is 0. So that's going to be about 10 meters per second. So we know that when the block reaches the bottom of the ramp, if I take this uh, fully 20 kilogram block, release it from the top of the ramp here, and let it go to the bottom with no friction. This 20 kilogram block going down that 11.7 meter ramp at an angle of about 31 degrees, the angle of the ramp, it reach about 10 meters per second when it hits the bottom. The reason why mass is important is because since F is ma, the acceleration will be less if the mass is bigger. You see that the mass is in the denominator. But we all know we push things. It takes more effort to push more massive things, get it started. Therefore, the lighter it is, the easier it is for that same acceleration to move it. So to end up going faster down that ramp when we let it go. Because the acceleration to be a little bit more uh, since the relative acceleration is fixed. In other words, gravity is pulling the same, but the mass will change. Oh, no, sorry. Mass actually cancels. I guess I'm thinking about friction. The different mass, so uh, if we did friction, well, that's where the coefficient of friction comes in. I don't think that'll change if the mass changes. What this is saying is no matter how massive the block is, it'll go the same speed, or at least acceleration prime will be the same. So I wonder where mass plays a part. Mass doesn't play a part here. Mass cancels there. But acceleration is actually dependent really only on the angle. Interesting. It does remind me of those videos I've seen where you have like a rock or something, and you have like a feather, and they put them in 0 G, and we know that the feather in the not 0 G but zero atmosphere, like in a basic vacuum, and we know that the two of these fall at the same pace. So, however massive the object is, given that this is frictionless, because um, the friction will appear apart. We know that if we have a sticky substance that we're trying to push, slide along the floor, it's going to be harder to push than the uh, uh, something that's not as sticky. And we know that something that's heavier will cause more friction pushing it. So we've all pushed something that is heavy versus something that's light. I suppose the reason why that doesn't uh, play here as far as the mass is because gravity is constant. If I'm pushing a block, my muscles will feel the difference between something massive and less massive. Uh, but gravity is just, from relativity, it's from the curvature of space. So it just pulls the same regardless. I'm also reminded of those problems where you have like a small vehicle and a big vehicle and they crash with each other. And let's say the total combined mass still ends up going this way because the bigger vehicle has more momentum. So that's where the mass comes into play, in that the acceleration on each is the same because the force is the same, but the mass is different. Actually, the force is the same, but the mass is different. So the acceleration on either are different. I guess it depends on the problem. So I guess we'll come back and welcome who's joining. Let me know if you have any questions. You can drop a line in the chat or join me on Discord. I guess later we'll get into one of these problems where we have the um, uh, two masses rolling along and crashing against each other. Because I have to remind myself of that physics. So that's the purpose of this course, is sort of a foundational course to remind ourselves of things, filling gaps of things we might have not learned as well, or remind ourselves of things we've forgotten, as well as better be able to teach the next generation of scientists the basics. So it's pretty cool. Now, we talked a bit about friction. I always hated calculating friction. We'll go ahead and do it. Probably because I'm starting to get better at it. And plus, it's good to know since friction is normally a part of the process. So the idea is with friction, uh, like the net force will be Fx, which is the force that pulling down minus F, which is the friction. Otherwise, right, friction is a sort of cursive F. So as the acceleration of gravity is pulling the mass down, friction is going to be slowing it down, and friction is always counted uh, in the direction opposite the motion. So it always occurs to me that things are not exactly perfectly smooth. So it seems like this box will be like hitting an edge and maybe will go upward a little bit, but technically that upward, I guess that'll be counted as the normal force or countering the normal force. So, but technically, I guess those things are so minuscule that we just ignore them. But it is interesting to consider. Uh, is there some component of normal force that's not, of friction that's not directly horizontal? What, neither here nor there. So, what we're doing it in this class is the friction force is going to be the uh, force of gravity, or the normal force, not the force of gravity, but the normal force times the coefficient of friction. So depending on the material that you have, it'll, you know, have a different friction. Like glass, we know we can slide things over glass better than we can do concrete or something like that. So this coefficient of friction will determine how much friction that object has. And the idea is that we use a normal force because this is the force that's balanced by this y force. Both, if it wasn't equal, it'll either be floating off of the ramp or to be sinking through the ramp. So we know that these two forces are equal, which is why it stays in contact with the ramp. So this normal force is the force that's putting it in contact with the object, and thus that force is directly proportional or directly involved in the friction. So if we tilt that ramp higher, the friction will be less because it'll be less normal force. And of course, if we turn it 90 degrees, then uh, what I mean, bump away from the ramp and just fall freely. So what we can do to get from the new force, the new net force acting on the object, is add these things together. So we know what Fx is. We calculated that earlier. That's what we didn't calculate it. We saw straight for acceleration. So go ahead and calculate that now. We have Fg sine theta minus 0.5 y mu. So that's going to be Fg sine theta minus Fg cosine theta mu. So that's going to be Fg sine theta minus mu cosine theta. And I think that's looking correct. Let's plug this in. So we have the mass was 20. Right, one more thing, one more step. Sine theta minus mu cosine theta. So we have the mass was 20 kilograms. Gravity 9.8 meters per second squared. And automatically we see that this gives us the units of newtons. Newtons are kilograms meters per second squared. That's the units of force. And now we have sine of 31 minus 0.5 cosine of 31. So let's see what the new force is and see if it makes sense. Maybe I'll put this as a lot to make it more clear. We have 20 times 9.8 with a 1 times sine 31 minus 0.5 cosine 31. Oh, I can type something in incorrectly. Let's see what I typed in incorrectly here. Theta u 9.81 0.5 cosine 31. So let's see what I did wrong. I did something wrong here. It is. I have my calculator in radians, but I'm putting in degrees. It's here every time. Change this to degrees real fast. Try this again. Okay, so that makes sense. So we have about 17 newtons for the net force given friction. So what we could do now is get the new acceleration given friction, which we know how to do. So pretty much everything here is the same process. So here, well, let me just show this step. So what I'm going to do is get this step here. So we'll say F equals M. I'll call this A double prime. So A double prime equals F net divided by M. So that's 17 newtons divided by 20 kilograms. That equals 0.85 meters per second squared. It's a big difference. Yep, it's about what I had last time. So as we can see, we can go through the same process that we did earlier. And, we have our new acceleration. We can do our integration. We can find how long it takes to get to the bottom with this new acceleration. We can plug the time into the integrated velocity equation. and get the velocity when it hits the bottom given friction. So the steps are there. It's a matter of plugging in a new number for the acceleration. So I would say that we've gotten that solved. So something else we can do, something that I was looking at earlier. So this is a bit of undergraduate classical mechanics right here that we just did. Why don't we look at a little bit of graduate classical mechanics, some of the things that we're talking about in graduate school, and then we'll wrap it out. So I'll actually add that into the text. Points. I'll say undergrad, grad. Right. So grad level stuff. So one of the things we talk about in grad school is the fact that, like an undergraduate, you talk about basically one particle, like we did here. Even though it's like a massive block, 20 kilograms, it's still just one mass. But what if you have a system of particles? What if you have hundreds of thousands of particles? Like, let's say a galaxy of stars. You all know I'm interested in astronomy. My focus in graduate school is an astrophysics focus. Let's say we have this galaxy of stars, and we want to know how we can understand the motion, how we might be able to utilize physics principles to describe the motion of each of these particles. So let's say we put a coordinate system here, and the difficulty is, of course, you have hundreds of thousands of particles. It'll be take a long time to go ahead and try to write an equation of motion for each of these things, because for every single particle, you would have F equals ma. Me roll on my notes a sec. It's like I saved the wrong file, but I could show you all this without looking at my notes. So let's say that we have our coordinate system here, and F equals ma, similar to what we did before, except this time it'll be Fi mi ai, and each of these individual particles would have its own, you know, force. So let's say, you're trying to figure out how this whole thing moves. If an external force is moving against it, you'd have to calculate each one of them. So basically what we'll do is we will sum up all of these to get the net force that's acting on this entire system of particles. And one of the things that we as physicists do to simplify this is to recognize that we can, when we look at the system of particles in this way and we sum them together, we can simplify it like so. So if we look at uh, this grouping of particles, we can consider that somewhere in this grouping there's going to be a center of mass. And what we find that center of mass is we can actually use a weighted uh, estimate or a weighted average of each of the masses and their positions in this system of particles. So, for instance, what we can do is we can create a new variable called R, which is the point of center of mass. And what we can do is we can sum the mass of each particle I, the the position of each particle I, and we can divide it by the mass of the entire system. And what this does is this calculation allows us to calculate the center of mass of the entire system. Another interesting thing is if you sum up all the masses of the system, you just get all the masses of the entire system. So if we plug that into here, we can see that the mass of the entire system times the center of mass position of the system is the same thing as the summing up each of the masses times each of the positions. So that's an interesting aside. So what this allows us to do is actually simplify the uh, uh, F equals MA to take into account the full system. So if I was to write this out for you all, let me recall, and I may actually just pull up my other notes. But thinking about it, there's a detail that I might be forgetting. Oh, okay, there we go. So one thing to look at as well is when you're looking at the system of particles, we can take and use integration to find out that kinetic energy and potential energy can be thought of in a certain way. So what I'm going to do is I'm going to actually um, derive what we're going to eventually plug this into. Uh, so what we're going to do is we're going to take this scenario here and we're going to look at it from a perspective of work. So work in the perspective of force is going to be integrating the force that's applied to an object times the position or the distance that that object is moved. And the interesting thing about force is that force in the instance of work is going to be the same value regardless of the path that you take. So this type of integral, when you're talking about work, is called a path integral. So let's say I have a box and I'm going to move from point 1 to point 2, and that box is in the gravitational field. Even though I may walk while I have this box, when I lift it up, the only work that I do is the work going from 1 to 2. And this is important because of two reasons. The first reason is if I look at uh, work going back to the MA, we can call this F equals MA. We could also recognize that acceleration is the same thing as the derivative of velocity, and momentum is mass times velocity. So we can also see that work is mass times the derivative of momentum. So what this allows us to do is plug this up in here, and we can see that work is going to be the integral 1 to of the dt mv dot ds. Now, and there's an interesting thing that we can do here to help utilize this simplification is to recognize that velocity is distance over time, meters per second. You understand that? So what I can do is I can divide this through and say distance is velocity times time. And if we're talking about an incremental distance, we can say ds is velocity times dt. and I can plug that into my integral. And I have work equals the integral 1 to d dt. I can actually pull my mass out, v dot v dt. Now, the interesting thing here is, and there's one detail about this that I'm still working out. I may have to ask my professor about it. But if I was going to take the dot product of this, v dot v, it's going to be v1 v2 dot v1 v2. So that's going to be v1 squared plus v2 squared. And we also know, we can say that if v1 equals v2, this is 2v squared. So if I was to put this together, I can say 1/2 v dot v equals v squared. And I'm still, there's a 1/2 that pops out here somewhere. Another thing I notice about this is, if we was to look at the magnitude of this, which is to say, the magnitude of a vector equals the square root of this thing that we have here. So the magnitude squared equals v1 squared plus v2 squared. And again, if I say v1 is equal to v2, like it was a 45-degree angle, it'd be 2v squared. And this may give us the same thing. And this is just v dot v equals 2v squared. Suffice it to say that if I was to bring this down and plug this in, I'll say work 1, 2 equals 1/2 m integral d dt v squared dt. And the derivative of an integral is just what it is. And now we can say that that equals 1/2 m v2 squared minus 1/2 m v1 squared. And we know that 1/2 mv squared is the kinetic energy. So that's t2 minus t1. Now, the last interesting thing I'll point out in the last 5 minutes is, since the work that we do on this system is depending only upon the endpoints, we can define a quantity that depends only on the endpoints, which we call potential energy. So what we can say is that work equals integral f dot ds, and we can define the potential with a capital V and say this is integral dv and they call it negative because the kinetic energy and potential energy plays a inverse role. So if I have a block up here and I drop it down, the more it falls, the faster it'll go, the more kinetic energy it'll get. But the less potential energy it'll have because it's lower. We put the negative on the dV. So that means that work also equals negative V2 minus V1, which also equals T2 minus T1 potential energy. So the last thing we'll do is put these together. We have V1 minus V2 equals T2 minus T1. So moving these things around, we can say that V1 plus V2 equals T1 plus T2. Oops, I wrote that wrong. We have to say V1 plus T1 equals V2 plus T2. So what this means is the total energy at the beginning is going to equal the total energy at the end, unless we know that the energy of a closed system is conserved. And by the way, what this allows us to do is recognize that the if we was to plug this into F equals ma, right here, what this will end up saying is that the total system behaves as if the mass of the entire system is concentrated at one point in the center, at the center of mass. And we could look at the system that way. So more details of this will come forward in the future, but it seems like enough for now. So those watching, if you have any questions, now is your time to let me know. And I'll go ahead and hop off with this science hour in a bit. And I'll be back again next week, if not tomorrow. Next week, Saturday, I meant to say, if not tomorrow, or if not through the week. But I'll definitely be back for Saturday of next week. I'll give you all a second for any questions or comments as I wrap up. Hey, what's going on, Push? Good to see you. Thanks for dropping the line. Let me know you're there. Hopefully everything I explained was clear. A few things I'm still working out. I'll get more details as I continue to progress. And we'll see what the subject will be next week. Let me know if you have any ideas. So thank you, Push. Thank you for everybody who watched. Thank you for dropping the line. I'll see you next Saturday for the next Science Hour, if not sooner. I hope you have a good evening.